than mostly repetition of things you've seen. So please, I would rather have that more as a discussion and points that you would like to go back. But most of my talk is going to go about the problem of the p-values. I know it's boring. I mean, the exciting stuff is the machine learning aspect. So you probably all know what's a p-value and so on. Except that the non-boring thing is most of the results are still going to be published because there's a p-value. Okay, so I just want to go and review a bit of those aspects because the problem is that we're still in a phase where those objects are still lingering and be there. I want you to make sure that you at least know what they are and possibly have the arguments to say to the reviewers or or the editors, hey, really we should do things differently. So one of the questions is was Ioannidis right? So how many people have actually read the paper Ioannidis, the 2005 why most results are false, wrong? So it's not that many people actually. I'm surprised. It's only a handful of people in that room who have actually read that paper. So please, after the talk, whenever, go and take that paper and actually read that paper. And I think that's really important. And most of it is not easy to read. And a lot of what I've done is actually to make it a little bit easier to understand and just be able to actually navigate that paper much more easily than you probably would have without those materials. So bear with me. You'll see a couple of notebooks. I'll show you a couple of notebooks that you can study after the talk. I'll show them quickly, and those things will be hopefully helping you. And if they don't help you, please, you have to tell me, and I'll correct, and we will improve those things. Right. So the problem is, I think, it's both technological or a methodological probably, and sociological. So the key problem is that the p-value and the null hypothesis statistical testing is just it's probably a very bad framework. It is actually recognized to be a bad framework. So that's the technical problem. Statisticians agree that this is not a good framework in general. And the sociological problem is that once you have set up that framework, it's just kind of impossible to get out of it. It's there've been after bans of APS was the latest. I think was trying to say, hey, we don't accept paper that has a p-value in it, which I think is ridiculous. I'll tell you why. But this is still so pervasive, and I still think that nobody understands the problem. So let's go for that. So that's the sociological. So is there a solution? We say, yeah. So I won't go again into the reproducibility crisis, but I will take a couple of examples because I'm sure, that I still encounter people who say, hey, this is not that bad. You can't be right that most of the results are wrong and so on and so on. But I think it is actually that bad. We just have to recognize it. Just don't thrive on it in some ways, but recognize it and see what can be done to actually change it. Reproducibility is a computational issue, replicability is a statistical issue. So I don't know if that distinction has been made so far, but I think it's kind of important to make it. When we're talking about reproducibility, and the word reproducibility usually takes both meanings somehow. If you read the 2011 Peng paper, for instance, it can make that distinction very clear. But in general, when people talk about the reproducibility crisis, they also talk about the replicability crisis. So you find a result in a paper, can you actually, if you redo that experiment with new subject or new setting, can you actually refine those things? I just want to plug a little quick thing here. It's all about generalization. It's all about generalization. So in some sense, if I want to reproduce a result, I kind of I take the exact same data, the exact same environment, the exact same, everything is exactly the same. I just have to push the button and that does the computation again, and you've learned about Docker and all those things now. And that's critical for making sure that you can go back and have those results again. to some extent, you kind of generalize in some ways. So you don't actually generalize, but you sort of like you can replicate in time with the same environment. That's what I would like you to say. When we say replicability, it's in Peng's world, it's really like okay, we now have a new set of subjects, a new set of participants. Okay, but then in fact, it could be how about we have a new scanner? How about we have a new set of stimuli, like that was presenting? How would we have a new environment, computing environment? This is not like Ubuntu 18.04. This is now like CentOS whatever, and what are the actual little libraries behind all those things the same, and are we going to get the same? But in some sense, are we generalizing with the different things that are across different things, and on what can we think we are generalizing? That is the problem. So statistics and machine learning somehow are like focusing on the generalization on the actual cohort or the participants, but very little on any other generalization. So I'll take you an example. I can't remember if I did this in my talk, and I'll probably go. I'm talking now like freely, so so I'm not following actually the talk. So this is how we will make it free form. But the thing that we never see, for instance, or almost never see in a paper is I've used FreeSurfer to estimate the cortical surface, and that generalized with ants, with FSL, and I've also used SPM to estimate that thing, and so on. Has anyone seen that sentence or like that sort of thing in at least one paper recently? I see Ariel thinking very hard. No? Not in imaging, or maybe in other fields that I don't know, but maybe that's in other fields. But that's a critical thing, because if indeed those results are not the same, are we generalizing across those methods? And when I say generalizing, maybe I'm kind of hacking and perverting a little bit the word. But in some sense, if we want to know whether a result is solid, we have to define in which direction it is going to be solid. And we have to define in the discussion. We say, okay, this is actually using that tool. We haven't checked. I would like to see somehow like we haven't checked that. It also does the same thing with this tool, and this tool, and this tool. Like, and you. I don't know if you've seen some of those preliminary results. Actually, FreeSurfer and FSL don't give you the same results. They just don't. Like if you're looking at the cortical surface, the cortical thickness in some of those areas, in some atlases, you have a correlation of what do you think is the correlation between those two software if you get it out of the box? Any first idea? For some regions, it's actually 0.2, 0.3. Okay, so that's not a great correlation across subjects. So you take many subjects, right? You measure the cortical thickness of the, in the anterior cingulate, and then you look at, whether that cortical thickness is actually correlated with the other software. Okay, and so I think part of the all this NeuroHackademy thing is giving you the tools to making sure that you can actually check those things much more easily than you. Because it's a huge work. If you don't have the tools, it's going to be a huge work to actually relaunch and do all those things. So if you had those, Docker things that you go, okay, I can now use exactly the same with the same data. I can use those tools much more easily. Yes, it takes some compute power, and you're learning how to use those things. And yes, it is possible now to do it in a reasonable time frame and check those results. Sometimes I worry that all those good advice that they seem really good, they're just going to slow you down. Right? It's going to take more time for you to actually write the paper, do the things. They're going to slow you down. I think Russ alluded to that. So there's a balance. I think we just have to keep reasonable. There's a balance, but we just have to know, and as a community, have to know that there is some kind of a critical thing that is going on that we don't check and we don't generalize to things that we think we may generalizing. And and that's so I think we are like in a phase transition period where things are still a bit in flux in how things are done. But the new standards in the future, I believe, will be that you will have to be checking on many tools, on the, not only replicating like the genetic people do. Okay, you do have to have a validation cohort. There's no way you can present a result and not have a validation cohort. I believe like if things go well in the neuroimaging world, and that's already we've seen that a little bit. You will, editors of serious journals will say, hey, no, you can't just present that specific cohort, that specific 40 subject. You will have to take another 40 subjects and replicate. And hopefully we'll see that things are replicated and so on, but not all of it will be replicated. Okay, so I've completely diverted from the talk. That's fine. Another thing that is important to notice here is that this p-value of 0.05, which is so, I call it evil, but it's not really evil. It's just a number. A number can't be evil, really. That's a physical. That p-value is really weak evidence. If you move to the Bayesian framework, if you look at how much that p-value for many H1 hypotheses, we'll go a bit over that maybe later on. But if you look at what is the base factor associated, what is the actual evidence that the data will provide you if you were to switch from a p-value to 0.05 to like a Bayesian framework where you look at the evidence, and that evidence is going to be fairly small. So it really depends, of course, of the H1 and so on. Yeah, but it's going to be fairly small in a very wide range of possible hypotheses. So that's the other thing is that and we'll see that there has been some proposal to actually change that threshold. Say, hey, that's really too weak. That's such a weak evidence. That we shouldn't keep that number. Okay, so the other thing is statistics are not just methods that you just use as recipes. And I think it was terrific to see Janet was before, because it's really about the practice of statistics. It's really how do you use those tools, and frankly you can't use them if you don't understand them a little bit. And I think that the whole teaching that is about understanding what are the things, what are we talking about, what's behind the scene, and taking the time to actually understand those things. So that's really the practice, and we see that those practice. So there's been a couple of studies actually many studies on practices. One of the old one, I think was already mentioned before, is the Simmons and Simonson Sim Psychology paper. And I think I have I may have but basically what Simmons and Simonson did was to actually study in psychology, what are the practice in statistics of psychology researchers. So they looked at, okay, how many times do you have three groups, and sometimes you're just going to drop a group and report only the difference between the two groups out of three, right? How many times do you do that? And so they went into another practice, like how many times do you actually acquire subjects until you get p-value of 0.05? How many times do you change the covariates when you don't get significant results? And hopefully those researchers were fairly honest and say, gave them the answers that where this is how this is a common practice that we do that so often, and so on and so on. And what they did then is to actually simulate, okay, let's take some null data, okay, and let's look at all those practices and see how the actual error rate is going to be changed with and without those practices, with what practices. So they established they have a beautiful table. I think I may have it later in the talk. I can't remember. They have a beautiful table of practice A, practice B, practice C, and so on. And this is the impact on the error rate so the thing when you're putting a p-value 0.05, what is actually the error rate, the type 1 error rate? And with those practices and with common practices, they went up to error rate of 60%. So that's where statistics are just statistics, but the practice and how they're used is so important, and why they're used and how that does. So that was like a shock to me when I saw that number, and then up to the point when you actually do and look at the actual simulation and say, oh yeah, that has that effect. But quantifying the effect of the practice was absolutely critical, right? Because otherwise we don't know what we're talking about. We know that's bad practice, but how bad is it? Is it like we're going to move like 0.05 to 0.06 and nobody cares? Or is it going to move 0.05 to 0.6 to 0.6? And half of the time it's a non-result. Okay. Wang, I think, et al., biomedical research, that was a very interesting study as well. They went and asked life science researchers on their they went to go and look at ask the biostatisticians that are interacting with life science researchers. And so those are a group of people that are getting asking for advice when you are writing a grant or when you're analyzing data and so on. So and they had like a fairly large sample for that. I think my memory is 90, 100. So not unreasonable, and meaning like you're going to interview those people and so on. And they ask how many times they felt that they were asked for things that were not legitimate and kind of pushed to actually get a result. It was absolutely abyssal. Almost every biostatistician that was asked for advice or was actually asked to provide results or ask for help for an analysis, every one of them almost was actually responding to that question. Okay, yes, I was asked to actually provide some significant result in a case where I didn't believe there was one. And so there's a very, very strong push, and if you don't, so there's kind of, and I think that speaks to the incentive and all those problems. So it's more like a social problem. But again, it speaks to the practice and sort of like we're living in a society where actually just knowing the tools is not how do we apply it and what are the incentives and so on is actually quite critical. I think actually it seems to me like Russ went over that example, but this is an example where 57 studies, the example of Müller et al. With the depression meta-analysis aspect, and basically that meta-analysis showed again that all the published papers that reported significant results were probably not actually reporting actual significant results. So it's one of those anecdotal evidence that I think are important. So I want all food cause cancer. Yeah, that's a funny paper. I don't know if you've seen that. Some of you have. I see some notes. They just took the list of food that were most common in recipes on the web. So I think something like 40 ingredients, ranging from broccoli to milk to whatever. And then they looked at how many studies described that this particular food item was actually increasing or decreasing the risk of cancer. And all of them, most of them, 75% of them actually reported significant results in terms of increasing or decreasing the risk of cancer, sometimes in opposite direction. But so it's and those things are feeding our society. You get the headlines on how many and more on all those media. You get all those headlines saying this. So p-value are getting more and more evil, right? So when that problem started to be addressed, actually right at the beginning, I think 1925, 1925, when Fisher sort of designed this null hypothesis testing thing, that was a time where a statistician and other people saying, hey, that's probably not a good idea. so it's also like a little bit the idea that we always think, okay, science is moving ahead and self-correcting and improving itself. That's probably not the case. Science is probably not that much, or it's much more slower than slow than what I think we all hope. So there's also like a very different conception of what's a p-value in the Fisher and versus the Neyman and Pearson world, right? How many people know that those distinctions? Do you know what's the difference between the Fisher approach and the Neyman and Pearson approach for a p-value? Yes? Raise your hand. 1%, 2%. Janet, you don't have to do that. We know you know. Yes. So very few. So basically, the Neyman-Pearson, which is a much more solid and appropriate statistical framework, is just setting a p-value as a decision-making process. You have to decide whether that's just a decision-making process. You have to decide, okay, I'm deciding a priori a threshold. Above that threshold, I will decide that I get something that is interesting to further look at. And that's probably just what it means. Interesting to further look at. Right. There's absolutely no difference between a p-value of 0.049 and a p-value of 0.00001, right? There's no difference in that framework. And all those sentences, marginally, very strongly significant, whatever, you can throw away in the basket, in the bin. There's no strong or small significance in that framework, which is the right framework. So just to let you know, as soon as you read marginally significant or strongly significant, just think, okay, those guys, they don't know what they're talking about. I mean, mostly, and it's fine. It's not a judgment call. We all of us, I'm including myself. It's just it's a perversive thing in terms of our kind of a society so which one is used today? Clearly the Fisher one, which is the right. Okay, so we all know what's a p-value. I'll just have to give you that test again. And I do believe that you'll be much better than the latest cohort because, All right, so we have typical research study, H0, no effect, and H1, there's some effect. Suppose the study result was that pass a test of statistical significance less than 0.05 in favor of H1, such that you reject the null. Okay, what has been shown? And I'll ask in increasing order, and please go ahead and please don't be shy. There's nothing is going to get out of that room. It's just I want a fair test. I want a fair okay. H0, so you reject the null. Oh, sorry. What do you say? H0 is false. Who says yes? That's what the test is saying. That's the result is saying. Nobody. Okay. H1 is true. I guess nobody either. It should be. Okay. H0 is probably false. 1, 2, 3, 4, 5, 6, 7. A good half of the room, I guess. Yeah, a good half. H1 is probably true. Okay, that's interesting. H0 is probably false, but H1 probably true is more problematic. All right. Okay, so interesting. Both 1 and 2, so we've eliminated 1 and 2, so let's eliminate that. Both 3 and 4, both at the same time, H0 is probably false, H1 is probably true. Right? No? Who says yes to that statement? No. Okay, it's a very interesting. I don't know. It is very interesting because I would have thought that people who say H0 is probably false would also have said H1 is probably true. Okay, that would be my assumption. And that doesn't seem to be the case. I have to find out why. People are more reticent for the H1 than for the H0 thing. Okay, and 7, absolutely not of the previous 1, 2, 3. Okay, so maybe a fifth of the room or something like that. Okay, so the right answer is 7. I was going to say the p-value doesn't tell you anything about the hypothesis. No, it just doesn't. It's not a probability on the hypothesis. it's another probability, but it's not on the hypothesis. So it doesn't tell you, and that's a really misconception that actually is, in real life you have to think, okay, what does it mean? What does it mean? So let's go a little bit in the details. So actually that test, that you took, it was given to medical students, and these were the results. So 1 and 2, as you see, get very kind of few results. 3 and 4 kind of gets like 30 and 20% result. For some reason, they also have like a bit more results on the null is probably true, it's probably false. That's interesting. And then 5 and 6, and very almost 5% of the medical. The problem with that is that the medical students they will make decision often on reading a paper and the results using that framework. Right? They will make decision on people, diagnostic and those things using that framework. So I think that's probably even worse in that population than for our, this cohort. That these things are not well understood, and also it's not even worse, but it's harder to correct as well, because because you're here and they're not. That there's So what's the definition of p-value? Probability of observing a statistic equal to one seen in the data or more, that is, or one that is more extreme, when the null hypothesis is true. So you assume the null hypothesis is true. So you can't actually talk about the probability of the null hypothesis. You know that null hypothesis is true, and you're looking at the probability of that statistic. What is a statistic? It's just a function of the data. You take the data, you take a function of the data. That's a statistic. So it could be the mean. It could be any number that you want from the from the statistic. And you've seen with Jeanette's talk, some of those statistics are kind of possibly more powerful. They would be more useful. Let's say you take a statistic that takes only 10% of the data. That statistic is probably going not to be really good, because it doesn't use all the data. So probability of observing the statistic equal to the one seen in the data or more, or one that is more extreme. So whether that's that t thing is actually is going to be the probability of that t being greater than that, or greater than a certain number when the null is true. Okay, that's the definition. It should be simple, right? It should be simple that we know all those things. What does it require? Knowledge of the null. So you assume the null hypothesis, and what is the most common null that we are taking in all our statistics? What is the most common null? And someone tell me. Sorry. Yes, but so let's say you're doing a Z test, or or even T test. What is the common null that people take? Right, but you have to assume a distribution. You have to know the distribution. You have to say, hey, it's not it's just you don't have just to know that those two means should be equal or different. You also have to assume the distribution of those means, and therefore the distribution of the data from which you derive the distribution of the means, right? So that distribution is most of the a lot of the time is going to be, okay, my distribution is on 0. Exactly on 0, and it's going to be a Gaussian or something like that. And then possibly you'll be a bit clever and make sure that this is actually look like a Gaussian, or you will test as often you will test. Oh, I don't have a significant my test on whether it's a Gaussian or not is actually not giving me a significant result, so therefore I can assume it's Gaussian, which is obviously wrong, right? Because the less data you have, the more it's using the test in the wrong way if you're doing that, right? Did I lose people, or did I not lose people here? Yeah, let's say you want to make sure that the test, your data are actually normal. How you do it. And many times you see in papers, I'm going to take a test to see whether there's a difference between my distribution and the null distribution and the Gaussian distribution, right? I don't see a significant p-value, therefore I can assume they are the same, right? But that's the wrong way of using a test, right? So that's those are really perversive. Okay, so knowledge of the null, which is kind of like a serious choice of statistics. Are like by the way, knowledge of the null. You're going to test whether that difference between those two groups is exactly 0, right? So you have you have two groups, I'm taking a simple example. You have two groups. You're going to test that difference is exactly 0, right? Okay. How likely the difference between those two groups is exactly 0? Is that likely hypothesis? Is that something that you can think of? Okay, that's something that. It's actually, if you have something which is quantitative and thing, it's actually the difference is exactly 0. The probability of that is actually 0. There's no chance. There's no chance. If you're having a continuous distribution, the probability of one specific point is 0, right? There's no mass. There's no, in measure theory, we would say, the mass on that set is 0. So it's so it's we're starting from a point where we're assuming something and we're testing from I want to see whether there's difference between 0, but that's the wrong null hypothesis right away, right? So I'm just Janet, please chime in if you want to reinforce or correct or. Anyway, so then there's the concept of the frequentist concept, where you have to imagine that you're going to repeat that exact whole study, it's the frequentist aspect, right? You have to imagine that you're going to repeat that exact whole study in the same way, so the same study design, the same sampling scheme, the same definition of statistics, and so on, right? So that's what p-value is. Imagine that all those things were repeated an infinite number of times. And what is the rate of getting a statistic more than that threshold, given all those things? And that's all right. So we go again. That's this is something that is real So let me talk a bit about power now. So you know what power is, or what's who can give me a definition of what power is, please? Yeah, or equivalently, the alternative is true. Yeah. So it's the probability of getting a significant test, given that you are actually in a situation when there is a difference. Okay. Why is power so important? Well, it is important and we'll go a bit on that later on. But it is important because if you have low power, you are not adding information to the scientific body knowledge. I mean, basically, that's my summary. If you have too low power, you actually, whatever result you get, whether it's significant or not significant, they are with a little bit an unbalanced aspect to that, but whatever. You're not adding knowledge to the scientific body. And computing power is complicated, and we'll go back with a little notebook. I still have 5-10 minutes, so I think I will switch to the notebook and skip the rest of the talk. But it's complicated because you need a lot of things. You need even more than what you need for null, for assuming all the null and the test, right? So what happens when you have low power? There is something which is called the positive predictive value, which is the probability. It reinverses the probability and moving away from the frequentist world to the Bayesian world. It's reversing the probability and saying, okay, what is the probability that my alternative is true, given that the test is significant? That's a much more useful thing to have, right, than the opposite. Because you're interested in actually doing an inference on the what are the results? I've done some hypothesis about something. What's the probability that that thing is true, right? That's a much more useful thing to have. It's actually absolutely not the probability of the test being significant, knowing that the H1 is true. Okay, because of the prior, because of if you go to the Bayesian world, that's so that's one thing. So when power is low, that probability is going to be low. That's one of the key results. right? So if you were to repeat this analysis, you'll get a low probability that to find the H1 is true. Inflected effect size. So with low power, if you detect something, absolutely sure that your effect size is inflated, and I'll show you why. It's there's the fact that it is detected. It must be that it is above a certain threshold, and therefore, if it's low power, it's let's say almost sure it's going to be inflated. But all those things depend on the probability of H1, alternative H0, and that's the complexity of the analysis of UNEDs. So it does depend on something which is called the odd ratio. So how likely is that H1 hypothesis? So the positive predictive value is depending on that, on this odd ratio, which is the probability of H1 over the probability of H0. And if H1 over H0 is like, say, this is a bit of risky hypothesis, but not too risky, I believe that there is about 20% chance that I will. That's a true thing. If you have a power which is on average, as Button et al. Was showing, which is something around, let's say, 0.3, that positive predictive value is already something about like 0.5. So it's half of the time you won't actually replicate that result, probably. Even though you had an actual significant test telling you, okay, that's less than 0.25, that's in that situation, right? And you've seen that before again. So with low power, high effect size, or actually variable effect size would be the thing, but all above the threshold that makes you able to actually publish it. And that's so I think you've seen that. Russ showed that, right? The effect size on the y-axis, year of publication on the x-axis. This is the influence of the BDNF on the hippocampal volume, and then the size of the cohort being the circles, the size of the circles here. And you see like a small little studies, high effect sizes, and therefore probably like a very prominent publication somehow, and then larger cohort, smaller effect sizes, and so on. Okay, so I think I would like to show you a couple of notebooks. I've got 10 minutes, 5 minutes. Okay, 5 minutes. That's actually. So there's a little thing that I've put on the an introduction. So it goes over, like, it takes a couple of definition. It goes over like it shows those classic tables just in case you don't remember them. This is the test is significant under H alternative. So your alternative hypothesis. So that's power. Power is 1 minus the risk of type 2 risk of not finding a result when in case you should find it, and I show also all those things. And then I'll go over a little bit of how you compute power. And I just want to show you that because that's a simple thing to do, but that's I think it's an illuminating thing to do. And before that, you need to have an idea of the alternative hypothesis, which actually does require that you have some idea of the effect size. That's one of the key things that if you don't find in papers what is the effect size, what is that number that you're saying is significant, and what's the how can I relate that to biology, and is that something that is actually visible in that framework of biology and so on. I can show you example of Science and Nature paper that don't show that, and actually we have a too small sample size. We would expect something like almost like 50% of the variance with like a simple SNP somewhere, like 50% of the variance with one SNP. That's just crazy. Like it's not biologically plausible, right? And you get those publications out. So please look at what is the effect size. And there are effect size can be sort of like a confusing sometimes. There's the kind of a rule. Okay, I've got two groups. Those two means mu1, mu2. That's the difference. The difference is in effect size. Now, if I normalize that by the standard deviation of the data, not the means, like the data, like just the standard deviation of the data. You can compute that. That's the normalized effect size. It's also called the Cohen's d effect size. So that's the effect size that often people report. They just normalize by the variation, by the standard deviation of the data, and then often you don't have the standard deviation of the data. They would provide you with the standard deviation of the means, or like something equivalent to that. And then there is a square root of n, the number of sample, right, that is going in. So that's the standard deviation of the mean is usually square root of n, like less, divided by square root of n compared to the standard deviation of the data. So so that's just a little simulation of how much Cohen's d should be. And so to get power, you need the non-standard, either the standardized or you need the non-standardized mu, the standard deviation, number of like the sample size, and the type 1 error. At what risk of error of type 1 are you working with? And the statistic, and the actual distribution, the distribution of the statistic. So I'm going to show you, so that's an example of how you compute an effect size. So authors find a p-value of 6.6 minus 10. They had 300 subjects. You can derive some kind of effect size from there. And this is how I do it. You look at the z value. That is the equivalent of the p in terms of the z. For that, I use a SciPy stats model and SciPy stats module. And you look at what's the z. And then you just divide by the square root, or multiply by the square root in that instance, or divide actually, to get the number, the actual number of, because that's already divided. That's divided, so you need to undivide that. So and that's and you get a z of 6 and a Cohen's d of 0.2, and that's giving you something because you know that Cohen's d of 0.2 it can have a small effect size. They had a lot of subjects. All right, so this is little like a plot of power. You can play with those things. The only thing I will want to show you is actually how do I compute power here, and that's only those 4 lines. First, you compute, what is the actual parameter of my alternative distribution. So I need the mu and the sigma for that, and just and the square and the number of subjects. So that's one thing. Then you're saying, okay, now that's my alternative hypothesis. Okay, I've got the parameter for that alternative hypothesis, and you just have to do a little bit of algebra to get that parameter. That's fairly simple, and then look at what is the distribution. So again, I love this little package, the stats package in SciPy, because you can create objects that are distribution. So that's a non-standard, non-central t statistic. So that non-central t statistic at that specific parameter for, and then I need the alpha. I need the threshold that I'm going to take the threshold for, right? And that's actually not the same, obviously not the same from the same distribution. That's from a normal distribution. Sorry, not the from a central t distribution in that instance. I'm using with t's. I could have done it with normal. That may have been a bit simpler, but in that case I want to make it a little bit like more realistic, and we are working with these because we have like a sample size of, let's say, 35, 40. And then that's it. And then you take the CD1 minus the CDF, exactly like in that, in this plot here. Where is my plot? Yeah. So you got the red line, which is the line that is the using the null hypothesis. What is my threshold? And then that's non-central t distribution is centered around that parameter that I've computed with the mean, with the standardized mean and the number of sample. And from there, I'm just computing that amount. What's the probability here? Which is the probability of being greater than that value, which is the setup by H0. So that's what is power. And if you can go and see, okay, have an idea of how you compute power and how you get a sense of what was the power of this analysis, which depends, again, number of participants, the type of distribution, the effect size, which critically the effect size, critically all of this, critically both effect size and, critically on everything. So if you have a good way of starting to go in those papers and say, hey, what is power there? Then that's I would be happy, because that's such an important skill to have. It's not easy. It's going to be sometimes very tough to know, have a sense of the power of a specific study, have a sense of the power of your study. I need to finish here. Thank you. There's a little notebook on positive predictive value as well. So if you want to know how that's computed and how to derive it and so on, there's a couple of lines of mathematics, like stats, to help you with that.